Okay, so we're going to continue about subnetting, a little bit talking about, again, IPv4 subnetting, about VLSM or various length subnet masking. But before I continue, I would like to share with you an educational idea for sure. And have any of you have heard about the law of broken couch?
No.
I mean, of course you haven't heard because I just made it right now. Okay, it doesn't exist, but it actually it tells you an idea. I'm going to include this link. It's a blog post I recommend you to read. But the idea is, you go, I don't know, you go to Home Depot and you buy a couch like that you can assemble. Okay, imagine that's the scenario. So you can assemble that, so you assemble it, and then you left with 1-2 extra pieces or extra screws that you don't have it, okay? You don't have it, but you feel the couch is still working, functional, you can sit on it, there is no problem with that. After a week or so, the couch start folding from the middle, okay? And it start become a little bit annoying, but still it's completely functional. You can see it with your friend, you can enjoy the time. No problem. After another few days, it start folding more. It becomes annoying now. You cannot sit properly on that. And at some point it gets broken. Okay. So what I'm trying to say is learning is also something like that. Learning is also something like that, exactly. You may learn things that we are talking. I'm not just talking about this class, on in general, all the classes, all the materials you're taking. At some point you may feel, I don't know, you get everything right, you're understanding most of the things, but you are missing some of them. You didn't really quite get well. Maybe by end of the semester you feel, okay, I didn't get that well, but I'm good with some other part of it. But then you might feel that, okay, that thing that you didn't learn well is making you problem, but not that serious yet. But later you go on with your study, you grow, I don't know, higher semester, then those basically broken pieces becomes more serious. Those things that you didn't learn at that point very well becomes real serious problems in your, I would say, later studies, later life or whatever. I mean, so then you might, basically that example is about the math that some people think they get, for example, linear algebra, they don't get logarithmic, for example, math, but they feel, okay, it's fine, you can proceed, but at some point, they start with a lot of other, for example, topic that they don't understand, but because of that broken piece, basically, that they didn't take seriously at the beginning, okay? So some people think, okay, I achieved my maximum, basically, capacity of learning math or any other topics that you might think of, and I cannot learn further than this. I reach my limit. Basically, there's no limit. There doesn't exist any limit. That limit that you feel is because of those broken pieces or missing information, missed pieces of information that you didn't get. So the law of broken couch tells us shaky understanding makes future concept hard. Eventually your couch collapses. So how to address that? You need to do self-reflection to make sure to understand, really to think about what you're learning. Okay, you need to articulate in your learning and basically all the process of your learning, and you need to seek for help. If you don't get anything right, seek for help from your professors, from the internet, from other reliable resources. So that's it. I just like to think about it by yourself, not here. Okay, that what is that those missing pieces in your knowledge? That hopefully there are not many. I'm pretty sure there are. Even at this moment that you're in the third, fourth semester, there are some missing pieces, but try not to let them just be, or just ignore them, think about them, articulate, and then seek for help not to miss them. Let's start with subnetting. Do you remember perfectly the subnetting that what we were talking? Any problem about that? Any questions? Okay, if there is no questions, let's do an activity. Okay. In the link that I sent you for the grade, okay, I appreciate if all of you, you open that link. The one I just sent in the chat, or the same link that you see your partial grades. What I want to show you basically is this. There are 4 questions, okay? There are 4 questions there, and I want to give you basically chance to answer those 4 questions in a group. I'm going to divide you in a group, in a like breakout rooms, in groups, and I want you to answer that, and then you earn basically 5 more grade, okay, for I add that grade in your partial to grade, okay, partial to exam, because there won't be any point in the grade, okay? Is that clear?
Yeah, but do we have to download the worksheet, or?
You don't need. You can open it online.
But if I make changes, wouldn't the changes be made for all of us?
You are able to make changes. In this, only in this sheet, you are able to make changes.
I mean, if I with my team work in the questions and I answer, wouldn't everyone else be able to see the answers?
It's fine, but you don't know what is the right answer yet.
Oh, okay.
Okay. So per problem for question 1, you need to put an IP, provide an IP address. Problem 2, 3, 4 are basically you point just which one is correct. Is A, B, C, D, E, F, or whatever it is. Okay, it's clear?
Yes.
Okay, so let me do the breakout room. I'm just going to stop recording. Okay. Yep, I'm recording now. So this one, you said B, the network part is
128.63.
And the host part?
2.100.
So this one, this is class C, okay. This one?
B, if I...
That's C again, right?
This is C again, right? This is class C. So basically what you remember is you need to remember the range of the IP address. I show you this table last class, okay? So these are basically the range 1 to 126, 128 to 191, 192 to 223, and 224. This doesn't matter, just A, B, and C. Remember those, okay? You remember A start from 0 and the network part, then class B start from 10 and network part, then class C 110 and the network part. So if you even just remember these 3 beginning basically, then you can calculate. If you forget the complete range, you can calculate it based on just knowing how they start. The first octet start with what, basically binary numbers. So let's go. So this is for basically second octet from right, or from the third octet. So if the question is basically if you consider all this for host, how many hosts you can have? 2 to the power of 9 minus 2, 10. So these are the things that we discussed. I just keep them in the slides so you can have more practice later. So let me go directly to the topic that we didn't talk yet, is this one. So basically whatever so far we were talking, we were saying, okay, for example, you want to divide the network to, for example, 7 subnets, right? Then you would consider you need 3 bits to have 8 subnets at least. So that 3 bits was giving you 2 to the power of 5 minus 2 number of the hosts, right? So basically, what we were doing with that barrel of apple in that example, we were dividing it equally to different size of basically basket, right? That was what we were doing. So what we were doing basically, sometimes they refer it as a FLSM or fixed length subnet masking. But what we're going to do is now study or talk about variable length subnet masking. So basically, the idea is subnetting a subnet. So we don't need necessarily to have a fixed subnet for all part of our network. We can have it in a different size. So that's what we talked before, same size of subnet. For example, this was, if you consider this as an example, we have one subnet here, one subnet here. No. One subnet here, one subnet here, subnet, one subnet. So let's say I would give this to you, then you would say, for example, you wanna, I don't know, you wanna have 8 subnet because for this WAN connection also you need that subnet. So what you would do here, you would have, like, for example, you needed 5 different subnets, one subnet for this, one subnet for this, and this, okay? And why I'm saying that, if you remember, if there is this, for example, graph in your exam, you need, this is a subnet mask here, you need a subnet, you need a network address from here, this one, this one, this one, and also 3 IP basically, or subnet for these links, okay? So basically the idea is when different LANs are joined each other through the WAN, okay, then you don't simply extend the LAN subnet to the new LAN. What you do is you define one subnet mask here for this communication, okay? Because this communication, this connection, or like even if it's wireless connection, is it going to happen through usually 2 switches, for example, one switch here, one switch here. And what you would do is you assign different subnet IP address for that particular switch here and switch here. So you design one, for example, you assign to this connection one subnet mask to have this 2 IP address. And another idea, there are a lot of reasons that you do that. One other reason can be, for example, you want a certain packet to know, for example, they are not from your network, they are going from, not from your local area network, they're going to the another local area network through a certain switch. That's why you define a subnet here. So if I give you this example, and they say, okay, design this, what you can say, okay, you say, I need 7 subnet, one for building A, building B, building C, building D, and for communication between building A and B, between B and C, and between C and D. So you want to have 7 subnets, but they are all going to be basically fixed. So you're going to have, you're going to do, for example, assign 3 bits, right, to have 8 subnets. But what we can do, let me see what I see. So basically, you might do this. Okay, you might say, okay, building A, you're going to have this network perfect because you need 3 bits for your subnets because you want 8. So this would be basically building A, B, C, and for example, this connection between router 1, router 2, 2 and 3, 3 and 4, and then you left with 1 subnet unused because you use 3 bits. You're going to have 8 subnets, but you are going to only, you're going to need 7 of them. You're not going to use the last one. And this is going to be host, okay? But here, the idea is you're going to waste a lot of IP address, available IP address. Because for this particular connection, you just need 2 IP address, okay? One here, but you assign 2 to the power of 5 IP address because you assign 1 total subnet to this, right? You can see this. So you assign basically all this range for this connection, but you're going to use just 2 of them. You're going to here also use just 2 and here just 2. The rest are going to be unused. But here, For example, if after one day, some days you're going to decide to make another 2 buildings, then you're going to be having problem because now you're just left with one unused subnet for your network. How we can solve this problem is using basically variable length subnet mask or VLSM. And the idea is just subnetting a subnet. That's all it says. So don't get confused with it. I'm going to describe how it works. So this is the previous structure. You have 3 bits. You decided to go with this subnetting. You pick 3 bits, and then you have 8 subnets of 30 hosts each subnet, right? So why we don't do this? We can use this type of structure. For example, you remember that even the example of barrel of apple, we said you can divide, for example, that 100 apples to baskets of 20 apples, then last 20 apples, that basket of 20 apples, you can divide it in 5 basket of 2 apples, right? So basically the idea is same. You want to do the subnet of subnets in order to manage the IP address much efficiently, not to waste them. So VLSM subnetting is similar to traditional subnetting. It's nothing weird here. I mean, don't get scared with the name. Bits are still borrowed to create subnets. The formulas to calculate the number of hosts per subnets and number of subnets created still apply, so nothing weird there. Still all those rules applies. The difference is that subnetting is not a single pass activity. You don't just get, okay, I want a network. My subnet is going to be, for example, 26. My prefix is going to be, network prefix is going to be 26. I'm going to use, or 27. I'm going to use just 3 bits. That's it. You can basically, the process can be repeated multiple times to create different size. For example, all these parts, you can basically do more with them. You don't need just to live with this. For example, you can get this and say, okay, I want to divide this to 2 different subnets, okay? Or you want to say this one, I want to do it to divide it in like another 4 subnets, okay? So you can do all those things. It's not just one time or one round activity. So it's a little bit history. In 1987, basically they specified subnetting. Subnetted network could use more than one subnet mask. You don't need to just use one round of subnetting. So that's basically it's started is VLSM, variable length subnet masking. So the whole idea is if you know how to subnet, you can do VLSM easily. There is no problem with that. Some people, I mean, the name is a little bit scary, but there is not really weird things happening there. So VLSM enables network number to be configured with different subnet masks on different interfaces. So basically you do the subnets are already subnet network address. You basically can have conserved IP address. You can use those available IP address, available range that you have much more efficiently. And it gives you a better hierarchical structure of your network. So let's go back to the example and see what we can do with this, okay? So this is the same example that we see. You have 4 buildings, 3 peer-to-peer connection between those LANs. So this was what we did previously. We said, okay, you want to do this here. These are basically IP range, number of hosts that you can have. The IP range basically for each subnet. So you assign this to building A. This goes to building B, building C, building D. And then you have now these 4 basically subnets to assign for these communications. Basically this peer-to-peer communication between LANs, and also that's all you have now. If you assign this tree, as we saw, this tree, if you assign this to this tree connection, then you only left with one subnet of 30 hosts. So you remember this WAN interface of the routers are assigned IP address. So you can basically what you can do here, you can, if you assign this subnet mask to the WAN address are just enough, right? Because as I mentioned, you need just 2 IP address or 2 hosts for this connection. Because imagine this connection would be 2 switches that are sitting here and here that are connecting to each other. So this subnet mask is perfectly fine for this connection because that's all you need, okay? So considering that, you can basically break your structure like this. So for building A, you consider this subnet. For building B, this one. For building C, this one. Building D, this one. Because this is exactly gives you the number of the hosts that you require here. For example, you would have 25. You need 20. That's the only option you have. In building C, you have 15. Remember, you cannot have 16. Okay, if you have 2 to the power of 4 minus 2, you get with 12. Sorry, with 14 hosts. So even for the 15, you have to go with this the subnet masking. For building 3, also the same. So basically, this is perfectly satisfies these 4 conditions for your building. So the idea is now don't assign all this big chunk of IP address to somewhere that you just need to have 2 IP addresses, use 2 IP addresses. So instead of that, get one of these, let's say this one, okay, and then divide it to a smaller number of subnets. So you get this, now you assign one of these small chunks to this connection between these 2 routers. For example, if this R1 to R2, you get this basically IP address. Is that clear what's happening here?
Yes.
Anyone has any questions, any doubt, any? Okay, so if it's clear, good. I hope it's clear. So the whole idea was not to waste all this like range of IP addresses. We get one of these subnet mask and we divide it. We subnet that particular subnet. So it's a subnetting of a subnet. So here you assign one of them to this router, another one with this subnet to this basically, and another one to this communication, to this connection here. So now what you left with is 3 subnet of 30 per host, and also here you have 4 subnet of 2 hosts each. So you have a bunch of basically available IP address to use. Remember that I said if you later you decide to make another 2 buildings like E and F here, and you have perfectly enough number of IP address to assign them. You can assign this to here, you can assign this to here, and then for this connection between them, you can assign one of these each. That's messy. Okay, I hope it's clear what I'm saying there. Any questions so far about this?
No.
Okay, so basically that's it. That's all VLSM is. It's pretty straightforward, nothing confusing, nothing scary really. You can see it's just the idea is subnetting a subnet. Okay. So, but what I want you to know is when you see this type of things, so you know how to, now you expect to use VLSM if it's mentioned in the exam or some other places that use VLSM, you know, you don't assign one big chunk of IP address here. Even if you can, you have available number of IP to do so, you don't do that, okay? So let's me go to talking a little bit about IPv6. So IPv6 addressing is not basically subnetted the way that we did with IPv4. If you remember, in IPv6, let me show you this. We show this basically the structure of IPv6, that you have these 48 bits that are assigned for global routing prefix. Then you have these 16 bits that assign for subnet ID. And then sometimes I said it might change a little bit, but usually that's the structure. 48 bits for global routing prefix. Subnet ID is 16 bits. And then you have interface ID of 64 bits. So you can see we have a bunch of basically range here. We can do a lot of things, even just considering this subnet ID here, 16 bits. We can have 65,000 plus subnet IP address here with this basically subnet. So that's a lot of subnets, and it's just more than enough. We can just go with that. So subnets created from the subnet ID are easy to represent because there is no conversion to binary required. You can, considering this you see here, it's not really any complication that we had in IPv4. It's not applies here. It's very straightforward when we're talking IPv6 subnetting. So for example, to submit the address of this, if this is our address of in IPv6, and this is basically that the prefix, now you have all these subnet mask. As I mentioned, you have 65,000 plus subnet network. Just considering this for the, remember here, I'm increasing here 1, 2, 3, 4, 5, but they are basically, each one is 4 bits, right? Don't get confused with that. These are basically hexadecimal values. So, but if that's not enough, that 16 bits are not enough, IPv6 also can basically bits can be borrowed from interface ID to create additional IPv6. I said 16 bits is like usually is more than enough, but if in case you have some weird network that you need more than that number of subnets, you can borrow the same way that we did in IPv4. You can borrow those bits and to have bigger number of IP address. So the idea is when extending the subnet ID by borrowing bits from the interface ID, the best practice is to subnet on a nibble boundary. Okay, that's what we try to do. Nibble boundary. A nibble is a 4-bit or 1 hexadecimal digits. So this is basically a recommended practice when we are talking about IPv6. If you need to go to interface part of the IP address and borrow some extra bits for your subnet, so it's the best practice is to take one basically 4 bits or a nibble, or basically 1 hexadecimal digit. So this is showing you that ID, So you get 1 nibble here, and now you can have more. Basically, this was the subnet ID part. Now you can move another. You remember this was 64 bits. So now we have 60 bit here for the network ID. This 60 bit. Because now we use this for subnet ID. So we get basically a nibble. So subnets can be basically grow when we are talking, because as I mentioned, if you consider taking a nibble from your interface ID, then subnets can increase by this, like 64, 68, 72, 76. So we don't really see, for example, 63 here, or I don't know, 67, 62, okay? So it goes like 64, 68, because we're considering for a nibble in, we're just considering borrowing 1 nibble here. Here we consider borrowing 2 nibbles, 3 nibbles, 4 nibbles, and so on. So that's for IPv6. Let me see. Oh yeah, that's it. So it's much straightforward when we're talking about IPv6. Subnetting. It's very straightforward. Usually we just consider this 16 here. If I go to the This one, this is the most clear one. Usually this is the part for subnet ID that we don't use. Most of the time we don't even need to borrow any extra bits from interface ID. The number that we have in subnet ID is just enough, as we can have 65,000-ish subnets. But in case if we needed to borrow more bits, we can go towards an interface ID, and each time we take one nibble or one hexadecimal value. This much is much more straightforward when we're talking about IPv6. So that's it from today. It's like the new things was VLSM, so you know how it works. The whole idea is subnetting a subnet. You don't need to have a fixed range for. You don't need basically to subnet your network just once. You can do it more than one time. You do the subnet, then you subnet one of your subnet in order to basically conserve more number of IP, don't waste number of IPs, and also have a better structure in your network. And also IPv6, that is way more straightforward comparing to IPv4. So if you get that earlier part about IPv4, VLSM is easy, IPv6 is very straightforward, nothing weird here. So any questions about VLSM, IPv6, even IPv4 subnetting? All clear?
But only when we use VLSM,
Okay.
we want to define a lot of subnets. We have to specify that we are using two different subnet masks, or only make every IP with one with /24, another with /story, for example.
No, if I ask you, for example, if I give you, I guess that's how you're going to see in your exam. I'm going to give you this, or let me see if I have a structure. For example, this one. You're going to see this, okay, then you're going to put IP address for it. So exactly what you see here. So what you see here is like that. You put this IP, this. If you want to do, for example, you take this one, you put this IP address, okay. If, for example, on top of this, or the part that is dedicated for this, then for this one, you put this one, this complete IP address. You have to mention this basically the prefix.
Okay, thank you.
Okay, this one is, then this one for this. Yeah, you have to put this, the range here, that number. Then it for prefix. More question? If there is not, let's close the session by talking about. So now you can read chat. Let me see. Announcement. So I already posted this. So you please put the summary again, 100 words minimum. Write about what we talked about, VLSM, subnetting, IPv6, and also read chapter 8. And these are the deadline for those activities, okay, for quizzes and for the exam. And now you can read chapter 8. It's the same thing that we discussed about more subnetting, VLSM and IPv6. Any question? So again, I really need to highlight this. These students, please do something. I mean, don't try not to miss any grade for the rest of the semester. Otherwise, you're going to have a serious problem, all these students, especially those. I mean, of course, the rest should do their things too, but those, they need to work extra hard. More question? Any question, doubt about grading, about?
Oh.